I'm not Ken Bishop, as this slide shows. Ken is our first speaker. I'm George Strawn. I'm the CIO at the National Science Foundation, the sixth position I've held there in the last 16 years, having come in 1991 following Doug Gale as the NSFNET program officer. That was prior to helping him, prior to that, helping him get MidNet off the ground. So I'm very happy to be part of this panel. And we've done a lot with bits and policies and protocols up to now, and now we're sort of going up in the protocol stack and talking about the impact of NSFNet and the Internet on science and engineering, which of course was one of the goals of the National Science Foundation. Being from the National Science Foundation, from the government and here to help you, I want to remind you of the contributions of the government. We've heard a lot about DoD's contribution with the ARPANET. I might suggest that for some of us, another important contribution was DoD's support of Berkeley Unix, which incorporated TCP/IP. And so those of us who had computer science department VAXs sometimes had our first practical experience with TCP/IP in the local area computer science networks on campus. That was certainly my case. And there's been one other government contribution that I'd like to just briefly mention, because it hasn't been mentioned up to now, which I think is probably pretty important in getting us where we are. And that was the U.S. government's orchestrating ATT divestiture. By creating a competitive market in long-distance telecommunication, the field was open for companies such as MCI and Sprint to join others such as UUNet and PSI to create a competitive market. And I think that was probably one of the important things that allowed us to get started and get going. The last thing I'll mention is one other dimension of the NSF's role in this activity. Someone on the last panel talked about getting together and trying to come up with a common proposal, and it couldn't be done. Well, that's more characteristic of the academic community or business competitors than anything else, right? So NSF was able to be put in a leadership position for this networking project. And that's using the definition of leader of getting people to go places they wouldn't or couldn't go by themselves. By coming up to a common direction, the NSF enabled the nascent spirit and energy of networking to move forward in a very vigorous fashion at that time. The herding of academics and industrial cats turned out to work pretty well. So as you know, NSF is in the business to find and support the best science research projects, or stated more fully, the best science and engineering research and education projects. And around NSF now, there's a lot of talk using the phrase transformative research. Looking backwards, I think we can say that NSFNet and the Internet has indeed transformed much of science, with obviously much more to come. We have a distinguished group of panelists who are going to comment on transformations in science from their perspective. You have their distinguished biographies in the program, so I'm not going to take away from their time to read them. I'm just going to tell you we have Ken Bishop, who is an emeritus professor of chemical and petroleum engineering at the University of Kansas, who is also an early user and promoter of our networking efforts. We have next to him Chris Greer, who is a biologist, faculty member who then came to NSF, first in a biology capacity, and then he got hooked into the data and information end of our business. And although it's happened recently, so it doesn't show in the program, we've recently loaned him out to the Interagency Networking and Information Technology Research and Development Group, where he is now director of the NCO, the organization which supports that, and co-chair of the NITRD organization. Next to him is Mark Luker, a former math and computer science faculty member turned CIO, and subsequent to that, EDUCAUSE Vice President of the Policy Office in Washington and in charge of such projects as NET at EDU and campus cyber infrastructure. Next to him is Dave Nelson, also started life as a mathematician. That's me. And physicist. went on to fame and glory both in the Department of Energy and NASA. The Department of Energy, he was one of the administrative leaders of networking activities and wandered into the CIO's office at NASA several years ago and is now setting his own agenda. Last, we will be joined telecommunication-wise with Harvey Newman, physicist from Caltech, assuming the connection still works, and we will see whether Harvey is still satisfied with 19.2 kilobits per second as it was announced earlier that he said he was. Without further ado, I'll pass the podium to Ken and then ask him to pass it to Chris, etc., so we can proceed.
Thank you, George. Good afternoon. Doug Gale has referred to me from time to time as his token scientist from the mid-net startup days. I prefer being the chemical engineering professor from Kansas who has always operated from a position of enlightened self-interest. Turns out that when I got my start, I desperately needed access to high-performance computing assets, supercomputing. And there was no real way to get it. And so I started out beating the bushes and doing, quite honestly, albeit passionate, not very well-directed activities. No, I didn't. I thought I'd lost the mic for a minute. My activities sort of morphed over time into what I now, with the power of time passage, refer to as, I participated in the 1980s effort to change the big telescope model of doing research into what I would call geographically distributed collaborative model. And that's basically the story I'm going to tell you today. Y'all know who GARP was, right? My apologies to GARP. You know, oh, there it is. No. Sue, we don't have any slides showing for me. I'm not sure. Is it F6? I'll let you do it. Thank you. I promise to keep my hands off it. You all didn't miss anything. All it said was that my name was Kenneth Bishop, et cetera, that George told you. I was wondering why nobody was really smiling about my apologies to GARP, but this is why. My remarks are going to be broken into about 3 different segments. Each one will talk about the intersection of a couple of fundamental activity areas. In this case, what I'm going to do is I'm going to talk about topical applications of computing as the intersection of science and computation. And the example I'm going to use is a wonderful example. It is the testimony given before a Senate committee in 1987 by John Connolly requesting support for an NSF program in networking. Are you getting volume on that? That's all I've got, Sue.
To study their basic nature and to project the effects of water policy decisions. Visible on the workstation screen is a map showing a river with a small city on its bank, 2 rural water wells, and the outline of an aquifer. The complexity of the models, together with the need for interaction with them, demands the use of supercomputers and high-speed computer networks. From his workstation at KU, Professor Bishop connects to a national supercomputing center in Illinois via a computer network. First results were displayed using contour plots to represent aquifer performance. These were obtained at network speeds of 2,400 bits per second in about 10 seconds. Each line represents a specific depth of the water table. The concentric rings show water flow from the river toward the wells. Although better for the scientist than tables of
Morphology
numbers,
is very
these
slow.
contour plots are but primitive outlines of a complex picture. Upgrading the network to a peak speed of 56,000 bits per second permits much more information transmission in the same time period. The added network capacity is used in various ways. The simple graphics format has been replaced with a color display of better resolution. A color key has been added to show water table depth. Red means a dangerously low water level. Blue means a higher level. The color display reveals a section of impermeable rock along the East Riverbank which prevents water flow to much of the aquifer's eastern arm. While improved, the scientist's view here is still not very clear. Raising the network capacity to 1.5 million bits per second, T1 speed, provides the power to focus that view in about the same display time. This increase in capacity has been used to quadruple the resolution of the picture, raise the number of colors to 256, and introduce the concept of time into the results. The actual nature of the water flow becomes apparent at this resolution, as does the city's effect on the aquifer. For the scientist, the march of time adds a vital dimension to the picture. Increasing the network's capacity to 44 million bits per second, T3 speed, and beyond, will support Professor Bishop's current research and guarantee its future development. This increase in capacity can be used to further increase the picture resolution to a level suitable for detailed policy planning, or to support animation necessary for developing answers to questions as yet unasked. Today, excellence in science depends on excellence in computer networking.
The first time I saw this graphic, it was in a document that was prepared by the NPACI program, and it basically showed the dreams for networking that we all can remember. I think it's interesting to note that in this map, not only do we see a network diagram or network map, but we also see 3 different clients represented: CIC, Sura, and EPSCoR. And we see the 2 PACI partners, NPACI and the Alliance. This was a very interesting time because this was when, as far as I was concerned, my applications took off. Again, the world according to Ken Bishop, we're now going to look at the intersection between science and communication, something I have called roughly science education. And what I want to talk about is the access grid, which is a creature of Argonne National Laboratory through the Alliance. And for those of you who are not familiar with the access grid, because it's only one of several different technologies that exist, it was a set of hardware and software technologies used to enable multi-site audio and video conferencing using the internet as a vehicle. 2 things made my heart beat. The first was the scalability of the access grid. And I'll show you a little bit of that with the next couple of slides. This, thank you very much. Let me leap to a whole series of slides very, very, very quickly. I do not know where that time went. I think we... George, let me stop there, because what I wanted to do is get back. The final slide was another world according to GARP, except it showed access grid, global networking, applications, and it was tied together, and it pointed to the triple intersection of those devices, which turns out to be my favorite topic of research, namely the, timing is blocking me, I'm sorry. The distributed calculation for the use in applications, and I'm going to quit, George, thank you. Chris, you're next, and may you not have the little difficulties that I had. See, it was escape and then Control Q.
That's good.
Sue, it didn't get there.
No, it's right underneath, I think. I think it's okay.
Are you okay?
Yeah.
Oh, it's behind. Got it.
Thanks, Ken. F5, one way to do it.
Cyber infrastructure. It's always the hardest part. Okay, I'm going to spend my time giving you the perspective of a user, and that was my role back in early NSFNET days. I was a biologist at the University of California at Irvine, working in the field of what then was called RNA splicing, was an example of genomics. And this chart shows a factor which is common now in science, the exponential growth of GenBank. And I brought along the 1988 version. This is release 57 of GenBank. And you see it comes with an efficient wrapper for interoperability. It has a nice search function. You turn the pages like this, and you can find everything that's in this notebook. And it has a file transfer protocol that works like this. All of you remember how that went. And I haven't a machine that could possibly read these disks anymore. So this has become something of a bookend. But this is the complete GenBank release, 22 million bases at the time. The most recent release of GenBank is 100 billion bases, would fill some 5,000 notebooks of this type. And to say the least, that no longer arrives in the mail. It's available online with a suite of tools and resources that make it exceptionally usable. And this growth in information volume and flux is not unique to science by any means. It's true of society as a whole. And these numbers come from an IDC white paper sponsored by the EMC Corporation to give you a sense of the volume of the total volume of digital information generated globally in just last calendar year. This is projected to increase a further six-fold by 2010, so an exponential rate of increase in the flow of information. And this surely has transformed, again, not just science, but society as a whole. And so we went from a world in which we all operated within 4 dimensions, 3 of place and 1 of time. And this, of course, had inherent limitations of geography and of time to access, to participation, to interaction. And you all have had the interesting job of beginning the process of building a 5th dimension, a dimension in which society globally now operates regularly. All of you carry around your connections to the 5th dimension, can't do without them any longer. All of our teenage children live through the MySpace and Facebook mechanisms and are familiar with this 5th dimension that includes computational capacity and capability in order to not just expand the feasible, but expand what's conceivable. The connectivity and access that NSFNET and its follow-ons created provide for reducing these barriers of time and place to participation and interaction, and then this explosion of information that provides the basis for innovation and discovery. And so we really do operate within a world of 5 dimensions. In the case of biology, this 5-dimensional world translates into a framework of science environments. And this framework of environments is built on top of a foundation of stable digital preservation and access organizations like the Protein Data Bank, like GenBank, PubMed, UniProt, and others. On top of this, since those organizations are reliable, have the confidence of the community, that enables the development of evolvable, extensible data standards, a set of tools for developing applications, and on top of that then are built a variety of environments for innovation and discovery. And the reason that the construction of this pyramid is possible, that anybody's willing to invest the time and the energy required to build a science environment of this type, is that that foundation of preservation and access organizations is reliable and persistent. This is just another view of the same kind of concept. This is the Molgenis framework being developed in the Groningen Bioinformatics group. And at the top layer are the interfaces, the protocols and tools at the lower layer, but importantly in between are the data hubs that provide the information on which the entire framework is built. And so the stability and persistence of digital preservation is key to the functionality of this fifth dimension. And so regardless of what definition you might use for Web 2.0 or Web 3.0 and so on, I think we are seeing a transition from the fundamental connectivity that drove the success of NSFNET and its follow-ons to one of synthesis, the ability to use a variety of different types of information in different contexts and formats together in innovative combinations for synthetic thinking. Given the volume of digital information at 161 exabytes, if every human on the planet divided up the job of reading those bytes at 10 per second, it would take 80 years to go through that volume of information. So, excuse me, clearly humans are not going to pour through all of this data, and rather machine access is becoming more and more important. And that means that simple text interfaces are becoming replaced by semantic context and a greater emphasis on understanding the relationships. And so it's an exciting world of 5 dimensions that was started with the NSFNET innovation, and it transformed my field of genomics. The way that science is done there is fundamentally different. And I think that transformation has just begun, and this construction process will continue into the future, and I'm looking forward to that. Thank you. And then F5.
Thank you. Good afternoon. I'm Mark Luker of EDUCAUSE. As you've heard and no doubt know in person, these technologies based on networking and the other IT infrastructure have provided the power tools for research and really revolutionized most disciplines today. We have access to computation data instruments in real time. You can digest and interpret information through visualization. We have communications to distributed disciplinary research groups around the globe, and we're growing into whole new cultures called e-science, cyber infrastructure, computational science. With this greater access to all of this, we can apply more talent to more problems and really speed the entire process. It's a total revolution. And our human organizations and funding models are starting to be adjusted accordingly. I was lucky to be at NSF for 2 years as the program director for NSFNET on loan from the University of Wisconsin. It was a time that you've heard about earlier today. During this period, we handed over the keys to industry, terminating the cooperative agreements for the ISPs, the NAPs, and the routing arbiter, and starting, in some sense, the commercial internet. That revolution is critically important for higher education, because although we can wire our campuses and between our campuses, our regional networks with very high speed, high quality networks as we have, we can't reach our students, our future students, our faculty and staff throughout the United States without going through high performance networking operated by commercial networks. So Broadband America, improving networking to every location in the country and the world, is critical for us. NSF didn't get out of networking at this time. They went into what was called high performance or advanced networking with a high performance connections program. This really raised the bar. It was a challenge to campuses. If you want this grant, put in a lot of your own talent and money. What else is new? And two things. You had to guarantee high-speed access to a real experiment that needed it. So the CIOs had to go out and mingle with the scientists, find applications, build project teams, and work that all into your application. And then the regional networks and, of course, the national backbone went in sync. And now all are no longer funded directly, but we have this new high-performance infrastructure. That's important because for the first time, we could do some of the real-time visualization and communications on a broad scale that was not affordable or manageable with the previous networks. During this time, there was also an effort to harmonize the federal research networks and a big public relations and outreach effort called Next Generation Internet, showing everyone how good it will be if we can only build it. Now, I'm going to focus on a different slice than you've heard before, and this is education. One of the most critical contributions to our research based on NSFNET and related technologies is in the education of our future research workforce, our future scientists and our future scholars throughout. And it turns out that there have been ideas about using networking and technology for education to improve the quality, for example, for many years. I started working in a psychology lab in 1966 where they were working on this, but it was with a engineering computer adapted to look like a workstation. The mouse wasn't invented yet. You had a light pen, and that was too heavy to hold your arm up for several hours. So the mouse was a big advance. The point of it, though, is those were experiments. They cost way too much. They didn't scale up. Even if they worked in the pedagogical sense, a university or other institution couldn't buy it and use it. What happened in the course of the NSFNET era is the technologies became affordable. They became higher quality, so ordinary students, not just geeks, would accept them and use them. And the networking made it possible to share them all and multiply the impact exponentially. So what are we doing now preparing future researchers? It's quite different than before. They can be involved directly in problem solving as opposed to memorizing and taking tests. They can be working in teams that are organized with flexibility and learning teamwork, by the way. And this organization is done through networking and IT databases, course management systems, and things like this. You can't scale that up with human teachers or teaching assistants. You can prove your skills in real-life situations, and for research education, this means join research teams, even as an undergraduate, sometimes in high school, and rub shoulders and participate with the professionals as they're doing their thing. Be useful to a real research project. And of course, develop expert thinking and strategies. I heard a talk by a physics Nobel laureate recently who mentioned that you could study physics for some 21 years with lecture recitation, textbooks, and multiple choice exams along with calculators, and not know how to be a physicist and not have much expertise. What you can do instead, though, in those days is come into the lab, work side by side with physicists, and in 1 or 2 years you're an expert, you think like a physicist. We can provide this now through these technologies at a much younger age and have a better research training. You've all seen virtual observatories. This takes real data, makes it available to everyone. They can not only make educational use, but actual discoveries. Remote instruments are networked for the purpose of research. The same networking can be used to support better education. Haptics, of course, developed for research, can be used to provide our research students, grad students and undergrads, different ways of learning short of textbooks and tests. This has moved out of the sciences now into, in this example, biology, weather, now humanities, and other applications. So I think one of the most critical issues is the research workforce of the future. NSFNET has provided a great quantum leap in how we can provide for that workforce. And you're going to hear a lot more tomorrow from John Seeley Brown, who's a world expert on this topic. Thank you.
Escape. I did it. This is an intelligence test, folks. There we go. Didn't do it. Try again. There. And F5. There. Good afternoon. I'm Dave Nelson. It took me a little while to figure out what I would say here because I was not an early user of NSFNET. I've always been a friend of NSFNET. But my early networking days were when I was a theoretical plasma physicist working at Oak Ridge National Laboratory. And in 1974, Al Trivelpiece, I think some of you know him, who was in the fusion program, decided that we need a computing network. So in 1974, I can still remember, we started doing dial-up, I think at 300 baud, to our brand new CTR computer center at Lawrence Livermore National Laboratory. Totally unclassified, by the way. Some people think it was classified. It never was. At that time, we started with a CDC 6600, and then within a year, we got a CDC 7600. Then we got leased lines at 56 kilobits a second in 76. And the neat part about that was they connected all the major fusion research centers, Oak Ridge, Princeton, Argonne, Livermore, Los Angeles, General Atomics, MIT, and so on. And I can still remember my awe playing. You know, we often get most awed when we're playing. But I would sit at the terminal at Oak Ridge, and I'd first log on to the Los Alamos computer, because we all had satellite computers. Then logging onto the Los Alamos computer, I would log on to maybe the GA computer. And eventually I had a daisy chain all the way around the country back to Oak Ridge. Well, just the thought that at the speed of almost light, speed of electrons, I was communicating made me sort of realize we can do something with this. I wasn't quite sure, but I knew we could do something. Just to say a little more about that, our networking protocol at that time was an offshoot of DECnet, which was deemed at that time more robust than the ARPANET's NCP, because remember, IP didn't exist in 1974. In 1979, as George said, I went to DOE to manage fusion theory and networking, and from then on have been mostly helping to make networks in general grow. But I did come at it from a standpoint of a scientist. And so the first effect of networking was our ability to do remote supercomputing, and therefore new science. We could do 2D plus time, or with approximate symmetry, even 3D plus time. And the things that I had before that, 1D was about all I could do, and 2D was, even 2D static was really tough. We used interactive computing systems, LTSS and then CTSS. There was a big fight over you're wasting the computer's resources because you're sitting there just twiddling bits doing your program development. And we users said, yeah, but we're worth something too. And we sort of won in that I think time sharing has become the norm. For us, it was the norm since, as I said, 1974. But it was a big fight. Now, the ability of the theorists to work together in remote supercomputing meant that we shared codes. And this paid off because when NASA and NSF started funding space plasma computations, many of the codes that we developed in Fusion could be taken over. We didn't worry too much about intellectual property at that time. I think scientists don't worry too much about it even now. But the second effect was the remote availability of experimental data. This was frightening because experimenters, those of you who are experimenters, really hold on to their data. It's their lifeblood. Until they get them published, until they wring every last publication out of the experimental data, they don't want to let go. But the theorists pressed, other experimentalists pressed, and we did manage, because they were all on the network anyway, to get people to start sharing. Now, my third bullet, I think NSFNET gets a real applause here. I remember when the Federal Networking Council was trying to decide what to do with the demise of ARPANET. I was at DOA at the time. We said, nah, we're a mission agency. We can't do that. Of course, DOD said, we can't do that. And it was NSF that stepped up and said, we'll do it. We will create NSFNet. We will take it over. The Federal Networking Council still had sort of a veto power, but NSF was the agent. I think this was especially critical because it produced a critical mass for TCP IP-based internet. Now, just let me remind you that going back to our networking at DOE, that in the 1980s, we expanded the MFE-net to become ESNet by merging with High Energy Physics Net, HEPNet. But there were protocol wars, serious protocol wars that threatened to torpedo the working together among, I'm going to remind you of some historical protocols, the MFE-net protocol, yes, we had our own, DECnet, ARPANET, anybody remember OSI, CLNP? I remember a review of NSFNet that concluded that as soon as OSI, CLNP was practical, we should go to that protocol. Remember that, folks? Okay, then we got into remote operation of equipment and facilities, but there were reliability issues which are still not completely completed. But again, going back to the Fusion program, it does remote operation of its experiments regularly now. Something that we tried, I don't think it's ever worked very well, distributed running of codes, that is sharing of codes among supercomputers in real time. The latency was just too large. It's always been a grand experiment, but I think we've showed that it has serious limitations, even though in a few cases it can add value. So what's going on now? Well, I think we're getting back to the people. And you heard from Mark and others about distributed collaboration. Email, video, shared data, Skype, you name it. But there is an issue, I think, that we are going to continue watching. It's the size of the video window. That's the talking head versus the data window. And in most things I've been associated with, the data window wins out. I won't go into the psychology. We could talk about that over drinks. But also then remote access to research results. That's one of the things that's not working very well. Since I retired from government, I'm doing a lot of fairly superficial research in areas that I wasn't familiar with, everything from metamaterials to flexible organic semiconductors, and I cannot get to research results. Informal access, yes, preprints, research websites, but access to published papers is far from a solved problem. There's serious, in this case, intellectual property issues that I think need to be taken care of. Let's look just for a last bit at the future. Thanks to things like the NLR are doing, Internet 2, and others, we're getting to very wide, dynamically adjustable bandwidth with high reliability. So we're heading into what I call the third generation internet at 10 to 100 megabits per second, end to end. That's why I say the entry into the third generation. First was dial-up with email. Second was low-speed dedicated or high-speed modem with 2D browsers. So with effortless video to the home and desk, you can imagine the human side taking on a new dimension. I could even think of a new Turing test. Is that thing I'm looking at a real person sitting right there, or is it an image? I think that could become real. I don't think I'm making this up. It's for the future, of course. And then finally, something that we're still not doing very well on, a trusted network with adequate security and privacy for research, for science, for education, for banking, for all those things that we need. We'll just keep slugging away at that one. Thank you very much. Now we'll see whether the
technological marvels of the day will give us Harvey via technical.
Hi, can you hear me?
We hear you, Harvey.
Good.
And your first slide is, your title slide is up, and if you say next slide when you want it, I will flip the slides for you.
Great.
You've got the podium.
Okay.
I did pose one question that you need to answer. Earlier in the day, someone said you had previously reported you were satisfied with 19.2 kilobits across the Atlantic. We want to know if that's still true.
Yes and no. The number might be right, but the units changed.
Ah.
Okay. Well, what I'd like to do very briefly and see how far I can get is to tell you in our field of science how far we've come, where we're headed, where we came from. The NSF had a lot to do with that, and how we're giving back. I won't have much time to talk about collaborative systems. You'll see a lot of what we do has really become global in scope. So too the collaborative system we developed at Caltech that you're partly looking at right now. So on the next slide, you have a picture of our upcoming scientific program. After 15 years, it's finally going to start running, Large Hadron Collider. And because of the leap in energy, we have a great panorama of possible new physics processes that we're going to discover, and we don't know which are listed at the bottom. You also see an indication of how global in scope our effort is. Thousands of physicists, hundreds of institutions, universities, and labs, more than 70 countries, and the number of countries continues to increase. So if you click again, you see that the real challenge is to bring all of this together, not only to allow people to collaborate, but to distribute, process, analyze, share data to make all these discoveries. Next. What's so exciting is the leap in energy. You can see the comparison in this one graph about comparing the collisions of the basic constituents as we know them, the quarks and gluons, towards the left of the plot at the present highest energy accelerator, the tevatron, and extending out to the right, a factor of many times higher energy, the Large Hadron Collider. Next. So there are many reasons to think that we'll discover new physics, and among the more exotic possibilities is we may have enough energy to produce black holes. Whenever I show this graph, I have to quickly add that such micro black holes are safe. They evaporate quickly. You also see a picture of Stephen Hawking and some of my colleagues who are waiting for us to produce black holes. Next. Well, so how to go about this? In fact, I guess I was one of the main people to formulate the kind of computing model and data distribution model that might support this scientific program. And so this is what it's evolved into, a worldwide ensemble of facilities, including many which are scaled to be manageable at universities, a few racks of equipment in clusters. And as you can see, the vital element interlinking all of this is networks. And in order to give sort of structure to it, I came up with this tiered concept, which is now a common language among physicists. But we also all knew that from the point of view of the single scientist, it's really getting at the data, getting at his collaborators and collaborating with them across this whole ensemble that is where the action is. Next. Well, what about the scale of networking? You know, the whole model is shaped by what we can do with networks. Being a physicist, and I guess it was the same when I was younger, working together with others in the early days of the NSFNET, it's a holistic approach where you kind of analyze the technologies, try to bring them together with other technologies, and see how much you can do and what are the limits you reach in trying to do your science. So this is the roadmap of networking that I developed in 2001, which we're actually following. You can see we progressed into the multiple 10 gigabit a second range for some of our links across the Atlantic, which I co-manage. We're experimenting in the 100 gigabits a second range, and we foresee reaching the terabit a second range realistically in the next 5 years or so, roughly. So we've experienced a growth of 400 to 1,000 times a decade, and it's going to continue. Next. Well, this is where we've come from. I really got involved in networking when I was working in Europe, and I was going to start working on experiments where the leadership was in the US, and therefore I really had a need for networking. It actually started in Hamburg, where I experimented with some of the public networks, some of the first packet networks of those days based on X25 were coming into existence. I moved to CERN in Geneva in 1985, and while there, we had our first link across the Atlantic, an analog link, which was microwave plus satellite at 9.6 kilobits a second. Then we went through many technology generations. Being a physicist and sort of agnostic, I learned about TCP, but I learned about a lot of other networks. We actually ran a 3-protocol network for the next several years until we reached this T1 link, which was provided by IBM across the Atlantic, the first all TCP link at T1 across the Atlantic. You can also see on the right the multiplicative factor as we went from our beginnings at 9.6 kilobits per second through the various generations. In 1996, following deregulation, we no longer were stuck with 2 megabit links. We used ATM until about 2002, when we started to have real TCP links without ATM. And we started to have wavelengths in 2003 to 4. And that's how we've been progressing in multiplying the number of wavelengths. So over a 20-year period, we saw a growth of a factor of 1 million times. And now things have slowed down a bit until the advent of 100 gigabit a second wavelengths, perhaps in 2010, and a bit later across the oceans, of course. Well, this whole picture has made our field not only users, but also co-developers of networks, because to justify this and to take advantage of this, we've had to become developers of networks. Next.
2-minute warning, Harvey.
Okay. Well, this is the outlook. Multiplying in purple is our network across the Atlantic, and in blue is the NSFNET network, and you can also see, as you know, which rides on the Internet 2 backbone now. Next. And this is the outlook that NSFNET has to go to 100 gigabit wavelengths, as I mentioned. And next. Well, this is just a sort of quick summary. Research and education networks around the world have followed these trends. And in many countries which I'm engaged with, you see this sort of progress. And also the commoditization of gigabit and now 10 gigabit Ethernet, which is equally important. Next. The other aspect is how to use such networks, and here our field has become one of the main developers, as I mentioned. We started to be able to fill links with TCP of 10 gigabits a second a few years ago, and last year we were challenged to make best use of a single link, and we did it in both directions. Particular developments, like one of my colleagues' development of the fast TCP congestion algorithm, and also an application in my group, have been critical factors recently. Next. So this shows 150 gigabit a second, the high watermark in a memory-to-memory exercise in 2005 at supercomputing, and next. And then storage-to-storage with our new application, being able to add up in a linear way by moderating the rate of sending data to the network and monitoring the network path in real time over long distances, being able to fill up links in both directions. And then at the bottom, I sort of estimated that a single rack of equipment could do 70 gigabits a second with one rack of low-cost servers. So that's what we tried this year, and so next. And so that was successful a couple of weeks ago. So this is on a few of the waves at supercomputing in both directions, 40 and 40 gigabits a second sustained from a single rack, completely storage to storage, combining our application called fast data transfer and fast TCP. Next. Well, we're building global systems. So we monitor networks, grids, some of the major research and education networks. We wrote a system called Mona Lisa, which has a lot of internal intelligence. And if you click again, you can see, click again. It's monitoring 1 million parameters at 340 sites in real time. We've also gotten into hybrid networking now. We rebuilt our transatlantic network in the model of Internet 2, based upon Sienna core directors so we can do channels with bandwidth guarantees. Before doing that, we've also built the software infrastructure to do this kind of dynamic switching. What you see is a file transfer going on. You can actually see the disk head moving in from the edge. That's why it goes down a bit. And then we emulate a cut on the fiber, and the transfer just goes on. Next. Well, finally, I wanted to say a little bit differently about how we're giving back. So we have these global collaborations. Networks are what enable us to make these global collaborations, and some of our international partners are not quite equal partners. And so we've reached out. We have a leadership committee called the International Committee on Future Accelerators. It appreciated the need for us to monitor the world's networks and look at trends. And one of the big problems we came across is this problem of the so-called digital divide, a different flavor of digital divide among different parts of our scientific community. So we've been going after that. Every year we give a world picture and we focus on this divide. Final slide, next. Final slide is this. So on our committee we also have someone, Les Cottrell, who monitors the world's networks since 1995 and divides up all the sites where he can ping the sites and look at availability and the achievable throughput using the Mathis formula that some of you know, and also more recently also trying transfers. And you can see the divisions among world regions. So I've been working on trying to bring those regions ahead, and we've made some progress in certain cases in Central Europe and also in South Asia. Okay, well, that's what I wanted to say. So I've taken you full circle, I hope in not too many minutes. Where we've come, where we came from. The NSFNET had an awful lot to do with the foundations of all of this and how we're trying to give back.
Thank you, Harvey. Please join me in thanking Harvey and the other speakers. See you all at dinner, and following instructions, get out of here.